15.147 has got an asterisk with it, which refers it back to probably a section has an asterisk with it. I think probably dealing with parameters. But anyway, we got a position of rod AB right here. It's controlled by a disc of radius R right here that's attached to a yoke there. And knowing that the yoke moves vertically upward with a constant velocity V naught, derive an expression for the angular velocity and angular acceleration of the rod AB. So I'm going to note a positive downward value for the position of this thing right here with respect to A. So in other words, the y-axis is vertically downward, and the velocity of C then would be given to us as minus V naught J, since negative J direction is up, and it said that this is moving upward. So all right, I want to look at this triangle that's got drawn right here. The contact point between the rod and this circle or circular disc, if you draw a line straight from the circular disc over to the point of contact, it will be perpendicular to the rod AB. And so you can see I've got a right triangle right here of an angle theta over here. So if I look at sine of theta for this particular thing, it's going to be equal to R over my Y position, Y being a positive number, and that's why I measured it positive downward like this. So Y is equal to, sine theta is equal to R over Y, or Y is equal to R over sine theta. And so what we want to do is derive an expression for the angular velocity and angular acceleration. Well, we can get that out of here if we take the derivative of y with respect to time. And the reason we want to do that is because we know what it is. We know what y dot is, in other words. So we'll take this expression right here and do y dot. And when you do that, you're going to end up with a minus cosine theta r theta dot over sine squared theta. And that's all equal to a minus v naught for the value of the y velocity. And so theta dot here is our omega, and so when you solve for omega out here, the signs will go away, and you'll end up with v naught sine squared theta over r cosine theta. And it is a positive number, so it is a counterclockwise rotation, which you can see obviously it's going to be if this is moving upward. Now, to get the expression for alpha, we would want to do omega dot. Now, the angular velocity is not changing direction, so it's just changing magnitude. So we're going to do omega dot. Then omega dot is looking at this expression right here and taking the derivative with respect to time. So when you do it for the top term right here, you'll get a 2 sine theta and then a cosine theta, which cancels out that one. And so that's why you end, and then a theta dot. So that's why you end up with 2 v naught sine theta over r times theta dot. The other one's a little more complicated because the cosine theta is down here, but when you crank it out, you'll get this expression right here times theta dot. And if you take a look at this, you can see that a v naught term is in each one of these. So we can factor out a v naught, and there's a sine theta in each term, and there's a r. So I'm going to factor out v naught sine theta over r. Well, that'll leave me a 2 times theta dot. Theta dot's right here. Notice the v naught sine squared theta over r cosine theta. So that's theta dot. So I'm left with a 2 right there on this term, and then v naught sine theta over r leaves me with these two terms right here on the other. And that right there, if you bring one of the sine thetas that you didn't use to factor out in here with this, you get sine squared over cosine squared, which leaves you a tangent squared theta. And so in simplifying this a little bit more, you can see that I can factor out a v naught over r out of both terms, that's squared. And then I'm going to look at bringing the sine theta over here with this, putting a cosine squared term down here with this to make this become a tangent cubed then. And if I put a cosine squared down here with this, I got to put a cosine squared up there. So I'd have a 2 cosine squared plus then tan squared would leave a sine squared because the cosine squared would cancel out the bottom part of that. And so we end up with an expression that looks like that. And you can see that I could take one of the cosine squared here and combine it with sine squared and get 1. And then that would leave me with the cosine squared right here. So I end up with 1 plus cosine squared there in the parentheses and a tangent cube theta.